if you want to solve this differential equation, y prime equals x squared over 1 minus y squared, and let's say we've got an initial condition as well. Let's say our initial condition for later is that y of 0 equals 5. So we can fill that in later. Any thoughts on how we could go about solving this differential equation? First of all, no, sorry.
We could multiply 1 minus y squared on both sides.
Yeah, because we've got a mixture of x's and y's here, but since it's all mixed together with either multiplication or division, separation would be a good technique here. Specifically, we can rewrite the y prime as dy dx. If we multiply both sides by the 1 minus y squared, that at least gets all of the y's and dy's on one side together. And what else would we want to do there to finish separating the variables?
Put the dx on the other side?
Yeah, if we multiply both sides by dx, so overall, we're multiplying both sides by 1 minus y squared and also multiplying both sides by dx. So we end up with a function of y, dy, equals a different function of x, dx. This is what it means to be a separable equation. If you can split it up so that you have just a function of y, or maybe just a constant times dy, equals a function of just x, or maybe just a constant dx, then that is a separable equation. And then how could you get rid of the dy and the dx?
Integrate.
Yeah, at this point, we could just integrate both sides. And once you integrate, then you'll end up with something about y equals something about x with no more derivatives or integrals, because you've actually evaluated them ideally. And at that point, you can isolate y and end up with, hopefully, y equals some function of x. So let's try that. We've separated the variables, and the fact that we are able to do that means we call this a separable equation. Separable equation for first order generally has the form dy dx equals something about x times something about y, or something about x divided by something about y, or something about y divided by something about x. As long as it's a function of x and a function of y combined with multiplication or division, then that means you can separate the variables. That's not necessarily the only way to solve it. There may be other ways as well. But as long as it can be written in one of these formats, something about x times or divided by something about y, that is a separable equation, and it should be possible to split it up like this. At that point, we just integrate both sides. And because of the way we split it up, we're effectively integrating this with respect to y and integrating this with respect to x. So the 1 minus y squared, what is that going to become? Integrate that, and what do you get?
Y minus y cubed over 3.
Yeah, y minus y cubed over 3. And then on the other side, x squared becomes?
X cubed over 3.
Right, x cubed over 3. And because we're looking for all possible solutions, not just one solution, what else do we need here?
Constant.
Yeah, we should have plus a constant. And you could put that on either side. You don't really need it on both sides though, because if you have plus an unknown constant on both sides, you can move them both to one side and combine them into some other unknown constant. So you could have plus an unknown constant on the left side or plus a different unknown constant on the right side, but you don't need both. So we've now solved the differential equation in the sense that we've rewritten it in a new format that has no derivatives and no integrals. All that's left is algebra. And ideally, it would be nice if we could isolate y. we'd like to get y equals some function of x. In other words, we call this an explicit solution. Explicit solution means you've actually got it as output equals a function of the input. What we have now is an implicit solution in the sense that we haven't yet isolated y in terms of x. And that's not always possible. Since we've got a cubic equation here, it's not necessarily possible to isolate y in a conventional sense. But we can at least say the function, the solution can be written in this format. We know how x and y have to be related to each other. Any questions on that so far? And we could also figure out what c has to equal. How would we find the value of c here? Yeah, we can use our initial condition because we know that we have a value for y, or a value for x and a value for y that should make this work. What we have so far is the general solution. This general solution is listing out all possible solutions. Presumably one of those solutions passes through the point 0.05 on the graph. So if we can find the solution that passes through that point, that is, if we can find the c value that makes this pass through this point, then we've got a specific solution. So let's try plugging that in. We replace every y with 5. Replace every x with 0. And then c is the only unknown left. We don't really even need to isolate c because c is already isolated over here. 5 minus 125 thirds. And we probably want a common denominator here. 5 is how many thirds?
(15 thirds), right?
So 15 thirds minus 125 thirds gets us negative 110 thirds. So if we fill in that value for c, we'll have our specific solution. So the specific solution that passes through this point, the initial conditions, specific solution would be y minus y cubed over 3 equals x cubed over 3 plus negative 110 thirds. So this would be our specific solution. It's still written in implicit form. We'd have to isolate y or isolate x to write it, to call that explicit form. But that's not always possible with standard algebraic techniques. So this might be as good as we can get. Any questions on that so far? And as long as you've got a reasonably advanced graphing program, and I think Desmos Online is good enough to do this, you can just type this in exactly as is, and it should be able to graph what the solution curve looks like. We could also get a solution curve by drawing out a direction field. You could pick some XY values, plug them into here, figure out what the slope is at each of those values, and then sketch the graph based on the direction field. Any questions on that so far? Or any other questions about this problem in general?
What happened with the intervals? He said something about the intervals today in lecture.
Sorry, what was that?
That each differential equation, I think, has like a interval, or you can get an interval from.
Do you mean like intervals where the solution is defined?
Yeah, something like that. That he would look at the initial equation, and then he would say that there's some like conditions that the function cannot be a value at certain point, something like that.
Yeah, there's the idea is that the differential equation itself might have some discontinuities in it. That there may be certain values of certain points for the initial conditions where the differential equation doesn't work. And this goes into an idea called the existence and uniqueness theorem, which is basically a way of checking, is it even going to be possible to find a solution to the differential equation before you even start solving it. And the existence and uniqueness theorem in the textbook is generally phrased as an if-then statement. The basic idea is we want to know if certain conditions are met, then we can guarantee that this initial value problem has a solution and only one solution. We don't want to accidentally run into a situation where, like, let's say you've got a differential equation and you've got an initial condition, x sub 0, y sub 0. Ideally, we'd like to be able to say that that differential equation with that initial value has one and only one solution passing through it. We don't want to run into a situation where we have a differential equation and an initial condition and it turns out there is no solution. And we also don't want to run into a situation where maybe it turns out there's multiple different solutions passing through that same point. Ideally, we want to have uniqueness. We want to be able to take the initial condition and find one and only one solution. We don't want to run into the situation where there's many solutions. We don't want to hit the situation where there's no solution. So the existence and uniqueness theorem is basically saying if certain conditions are met, then we can guarantee, yes, there is a solution that goes through that point and only one. There's no ambiguity. So let's take a look at that as an if-then statement. The then part, then the initial value problem, has one and only one solution. That's what we want. The if part is basically just a list of conditions that are required in order for that to work. If, and ultimately the initial condition, or the requirements here have to do with continuity. If you're talking about a differential equation where this piece, the dy dx equals that piece, if that piece is continuous, and also one more condition, its partial derivative, as it turns out, has to be continuous as well. The format we're going to use here, we're going to call this thing f of x and y. F of x and y is basically just the other side of the equation. If you've got an initial value problem that looks like dy dx equals some function of x and y. So you want to put it in that format first. Isolate y prime, so you just get y prime equals something about possibly both x and y. If that something is continuous, if f of xy is continuous, and it turns out that its partial derivative also has to be continuous. Partial derivatives, specifically with respect to y, are both continuous. And they don't necessarily have to be continuous everywhere. They just have to be continuous on some region. But the important thing is that region has to contain the initial value. If the initial condition is not in that region where this function is continuous, then that's not very useful. So we require this function and its partial derivative to be continuous on some interval, not necessarily just an interval, but some region of the xy plane that includes the initial condition. Then, if those conditions are met, if the function and its derivative with respect to y are both continuous on some region of the plane that contains the initial condition, then the initial value problem dy dx equals f of xy with the initial value x naught, y naught has one and only one solution on that region. Beyond that region where it's continuous, we can't guarantee anything. Maybe we cross over the border of the continuous region and it splits into many solutions, or maybe the solution just stops there and we have no solution beyond that. Or maybe it does have one and only one solution beyond that point. We just can't guarantee anything outside the continuous region. So this overall is called the existence and uniqueness theorem. In the sense that it guarantees that a solution exists and that there's only one solution. The solution is unique on that region if these conditions are met, if the function and its partial derivative with respect to y are continuous. Any questions on what that's saying so far?
Could you go over this theorem again? What does it mean again?
Yeah, the theorem is claiming that if you've got some initial value problem, like the one we have here, we've got y prime equals something about x and y, which we're just going to call f of x comma y for now. And we've got an initial condition, a point that we want the solution to go through. The theorem claims that if that f of x, y function is continuous and its partial derivative with respect to y is also continuous on some region of the xy plane, doesn't have to be everywhere, just some region that contains the initial condition, 0, 5. If that condition is met, then we can guarantee that this initial value problem has a solution and only one solution. There's no duplicate solutions in that region of the plane that we're talking about. So let's try that. Let's try applying the existence and uniqueness theorem to this function. That means we're going to need to check, is this piece, this x squared over 1 minus y squared, does that have any discontinuities? And also its partial derivative, does that have any discontinuities? So let's try that. We've got our f of xy. Let's find the, let me put the initial condition up here. X naught equals 0, y naught equals 5. And let's try writing out the partial derivative also. How would you take the derivative of this with respect to y?
Leave x as a constant and then differentiate.
Yeah, we can treat x as a constant. We're just treating y as the variable we care about. So we're just taking the derivative as if x is a constant, which basically means we can just pull out the x. We can just treat this as x squared times 1 over 1 minus y squared. So since x is a constant, x squared can be pulled out, and we just have x squared times the derivative with respect to y of, in fact, it might be easier if we just write this as 1 minus y squared to the negative 1. Yeah, we could now treat this as chain rule because we have the outermost function would just be to the negative 1. And then we've got this inner function, 1 minus y squared, inside that. So looking at the outermost function first, the to the negative 1, what's the derivative of something to the negative 1 power? If you were just taking, like, let's say the derivative with respect to u of u to the negative 1, what's the derivative of u to the negative 1 with respect to u? Yeah, you can pull out the exponent as a multiplier and then decrease the exponent by 1. So we're going to get negative 1 minus y squared to the negative 2. But then also, because of the chain rule, as you pointed out, we're going to have to multiply by the derivative of what's inside, specifically the derivative of that 1 minus y squared. So what's the derivative of 1 minus y squared? Yeah, negative 2y. So it looks like we end up with the negatives cancel out. We've got an x squared and a 2y in the numerator. And then 1 minus y squared to the negative 2 is the same as 1 minus y squared to the positive 2 in the denominator. So overall, it looks like our, oh, I forgot the squared on the x there. looks like our partial derivative with respect to y is 2x squared y over 1 minus y squared squared. And you can also get that from the quotient rule, by the way. You can treat this as x squared minus x squared divided by 1 minus y squared. You could take derivative of the top times the bottom exactly as is, minus derivative of the bottom times the top exactly as is, all divided by the denominator squared, and you get the same result. So there's several different ways you could go about this derivative. Either way, though, we should end up with 2x squared y over 1 minus y squared squared. So that's f of xy and the partial derivative of that f function with respect to y. But all we really care about is not so much the actual function itself. All we care about is where is it continuous. So let's check that. This function itself, f of xy, does this have any x or y values that make it discontinuous? Yeah, when y is 1 or -1, we end up with division by 0. You can't have divided by 0, so that means y cannot be 1, and also y cannot be -1. And if you don't see that right away, you can try just setting the denominator equal to 0 and then solving for y. So we get f is discontinuous if y equals 1 or -1. And it looks like it's continuous everywhere else. There aren't any other y values that lead to division by 0. And x only shows up in the numerator, and you can take any numerator you want. So it looks like x can be anything. There's no discontinuities as far as x is concerned. Other things you want to look for, what are some other functions that have discontinuities in that you should look for? What are some other values that can't be used as inputs to certain types of functions? Yeah, square root. If we're restricting our mathematics here to just real numbers, which we are for the moment, you can't take the square root of a negative number. So that means anytime you're dealing with the square root, you should consider only 0 and positive values as inputs. Negative values will lead to discontinuities on a real graph. Also, logarithms are important to look for. Logarithms can only accept what sort of values as input? Yeah, only positive values. If the logarithm has an input that's 0 or negative, it doesn't work. So that's another thing to look for. Anytime there's a logarithm, the input has to be positive. Anytime you've got a ratio, a fraction, the denominator cannot be 0. Anytime you're looking at a square root function, or in fact, any even root, square root, fourth root, sixth root, the interior can't be negative. Questions on that so far? Go ahead.
Oh, I had a question on like the intervals. Are we supposed to find where it's discontinuous at f, or when like we solve it in y in terms of x?
We're specifically looking for where this piece, the whole f of xy, is continuous or discontinuous. And so far, it looks like the only discontinuities are when y is 1 or -1. Everywhere else, it's continuous.
Oh, okay.
And then it looks like the partial derivative, this doesn't really introduce any new discontinuities in this case. Sometimes it does. You got to take a look at the partial derivative and check, does this introduce any new discontinuities? But in this case, it doesn't. It looks like the only discontinuities here are still when y is plus or minus 1, and we already covered that. So f and df dy. So the only discontinuities for either one are y equals plus or minus 1. Any other questions on that so far?
Yeah, so on the direction field, so like what does that represent on like direction field? Would it be like a vertical line, or would it be like a hole? Would it be like a hole?
I think in this case, if you have x being a non-zero number, but the denominator turns into 0, then yeah, on the direction field, that would look like a vertical line. But there's some ambiguity there, because if you have a graph that goes purely vertical, then there's some ambiguity about which direction it goes after that. And also, it's not going to be a function anyway. If you have it turned perfectly vertical, then it stops being a function, because it's going to fail the vertical line test when it curves around. So we're basically just looking for, under what circumstances can we guarantee that there is a solution that is a function? That's really the problem we're looking at here. Any other questions on that so far? So if we sketch out this region on a graph, we've got everything except for y equals 1 and -1. We can look at that on a graph, just an ordinary x versus y axis, or t versus y, or whatever the variables are. It looks like all x values work, but we've got problems at y equals 1 and y equals -1. If you graph y equals 1 or y equals -1, what does that look like? What would the graph of just y equals 1 look like?
A horizontal line.
Yeah, we just get a horizontal line at height 1. So this is one of the discontinuities. And likewise, y equals -1 would also be a horizontal line. So these are the only regions, these dotted red lines are the only regions where the original differential equation has discontinuities, which means everything that's not in those red lines works. In other words, we've split the entire xy plane into how many regions here? If you think of these as some sort of border or boundary, how many regions have we just split the xy plane into? Yeah, 3 regions. We've got the region above y equals 1, the region below y equals -1, and the region in between. And these are all infinitely large regions. They go on forever to the left and right. But a given solution can only be guaranteed to exist within one of those regions. And to choose which one of those regions our solution is going to exist in, what do we look at? How can we tell whether our solution is going to be up here or down here or in the middle zone? Presumably the differential equation has infinitely many solutions, right? How do we narrow that down to just one solution? Yeah, we go back to the initial condition, the point 0, 5. So we take a look at our initial condition, 0, 5. The initial condition tells us that we start up here, and that puts us in the upper region in this case. So that means because of the existence and uniqueness theorem, and because of the fact that the initial condition exists in some region where the function and its partial derivative are both continuous, that means we can guarantee that this initial value problem has a solution and only one solution in this upper region. But we can only guarantee that in the upper region. If the solution, in many cases, that just means the solution is going to have an asymptote there. Or it might mean that it crosses over, but beyond that, maybe it splits into multiple solutions. Or maybe it goes on, but just doesn't count as a function anymore. We can only guarantee things up to that point, though. We can only guarantee things from the initial condition in both directions, but only up to where it reaches the border zone here. We can't guarantee anything past that boundary. So in this case, we would say, yes, we can guarantee there is a solution and only one solution on the region above y equals 1. Or you could even just describe that as an inequality. We can guarantee a solution and only one solution for the region y is greater than 1. But x values could be anything. Any questions on that so far? Or any other questions on the existence and uniqueness theorem in general? Also, what if the initial conditions, let's say we had x naught equals 3 and y naught equals 1. In that case, what's going to happen? Where would the initial conditions be on the graph here?
It would be on the border, so we don't know if there's like only one solution.
Exactly. If the initial condition is on one of those discontinuity borders, then that means we can't guarantee anything. The if part isn't true, so we can't really tell whether the then part is true or not. The if then statement doesn't really tell you anything in situations where the if part is false. So if the initial condition is on one of those discontinuity boundaries, then maybe there's a solution, maybe there's many solutions, maybe there's no solution at all. We can't tell just from the existence and uniqueness theorem alone. We might be able to get an idea if we take a look at the direction field, but we can't tell whether there is a solution or not from the existence and uniqueness theorem. Any other questions on that so far? All right, then let's take a look at another differential equation where I think the solutions are going to be more interesting to predict with a certain other method. Oh, actually, one other thing about the existence and uniqueness theorem. The existence and uniqueness theorem becomes a lot easier to use for specifically linear differential equations. If we have a linear first order equation, that means we're going to have a y prime, of course. We could have a y. And those could be multiplied by, what could those be multiplied by and still count as linear?
Any function that doesn't have y in it?
Yeah, any function that doesn't have y. So let's say a of x and b of x and equals c of x. So we're basically just taking a linear combination of y and y prime using functions of x as our scalar, or functions of t, or whatever the independent variable is. And then we'll want to put that in the appropriate format, y prime equals something. But that something, we can just subtract this from both sides. And then divide both sides by a of x. And of course, this does require that a of x not be 0. But the thing is, if ax is 0, then this doesn't have a derivative, so it's not really a differential equation in the first place. So we're assuming from the start that a of x is not 0. The thing is, though, if you just take negative b of x over a of x, as long as a and b are just arbitrary functions of x, what do you get if you take a function of x divided by a function of x? If you got an arbitrary function of x divided by some other arbitrary function of x, what's the result going to be? Is that still some function of x, or have we introduced any new variables? Yeah, it's still a function of x, right? This whole thing is just some other function of x. Let's call that, let's say, p of x. And likewise, c of x divided by a of x is some other function of x. Let's say g of x. So that means in this notation, as long as you can write your linear first order equation as y prime equals some function of x times y plus some other function of x, this whole thing is now our f of x comma y. Are there any y values that would make this discontinuous? Are there any y values you can't plug in here? If we wanted to apply the existence and uniqueness theorem. Yeah, there's no discontinuities at all. No discontinuities at all for y. All y values work. All y values are continuous here. So that means when we're talking about regions of the xy plane where it's continuous, we don't have to worry about y. All y values are continuous. All we need to worry about is x values that might make p of x or g of x discontinuous. Which means instead of looking at regions, we just have to look at intervals of x values. We can look at just the x-axis and ask yourself, does this have any discontinuities? Does this have any discontinuities? So you just need to check, do p of x or q or g of x have any discontinuities? And the partial derivative is even easier in this case, because if you take the partial derivative with respect to y, what's the partial derivative of all this with respect to y itself? If you remember, we're treating x as a constant. What do we get?
Would it be the same?
It's mostly the same, but what drops out there?
The y?
Yeah, the y drops out, because if this is just a constant times y, the derivative with respect to y is just that constant. And then this is just plus a constant. Derivative of plus a constant is 0. So the partial derivative of f is just going to be p of x alone. That doesn't introduce any new discontinuities. It still doesn't care what y is. If p of x has any discontinuities in terms of x, we will have already covered that here. So we really don't even need to check the partial derivative in this case. All we need to check is these coefficients, p of x and g of x. If those have any discontinuities in terms of x, then those will be the boundaries on our regions of continuity. If these are continuous everywhere, then that means we can guarantee a solution everywhere. So the existence and uniqueness theorem becomes much simpler if we're looking at a linear differential equation. Instead of having to check regions of the xy plane where f and df dy are continuous, we just need to check intervals where these coefficients are continuous in terms of the x values. So in that case, you're not looking at regions of the plane, you're just looking at intervals on a number line, specifically intervals on the x-axis. So just checking where are those continuous. So what I would do in cases like that is, first of all, write your linear differential equation in exactly this format, y prime equals something times y plus something. Those somethings should just be functions of x or maybe even constants. Check if those functions of x have any discontinuities. And I would just write out just the x-axis. If they have any discontinuities, maybe you've got discontinuities at like, I don't know, 3 and 5. You would mark those as forbidden points. And then this restricts us to, let's say, 3 regions of the xy plane. Sorry, 3 intervals of the x-axis. Maybe everything to the left of 3, or everything from 3 to 5, but not including the endpoints, or everything to the right of 5. And as usual, which one of those intervals you choose is going to depend on your initial conditions. But the nice thing is you only have to care about the x value. You only have to care about the x value of the initial conditions. You don't have to worry about the y value at all. So that's the simplified version of the existence and uniqueness theorem for linear first order differential equations. You've got the same then part. The then part is then there exists one and only one solution. But the if part would just be if p of x is continuous and g of x is continuous on some interval. Any other questions on that? Or any other questions on these first order equations in general? And we're also going to get to some similar existence and uniqueness stuff later on in chapter 3, I think, when we get to second order equations. The main difference with second order equations is you need more information. You're going to need, as it turns out, 2 pieces of information instead of just 1 piece of information for the initial conditions. Usually for a second order equation, you know the, let's say the y value at position, or y value when the input is 0, and also the y prime value when the input is 0. So this often in physics situations, this would often mean you know where the object is and how fast it's moving, position and velocity at time 0. And of course, it doesn't have to be time 0, it's just that that's usually the most convenient time to use. Any other questions on that? All right, then that's it for today. Feel free to ask online if you want to request any topics for next time, if you have any other questions, and I will see you then.